This is a quick and dirty on-the-fly video, so please forgive me for my errors. We're going to cover Earth's interior, plate boundaries, types of boundaries, plate relative motion, and detecting plate motion. The Earth's interior is oftentimes thought of as just kind of a static series of shells, and this is the model of Earth as it might have existed up to maybe 1940 or so. It had an outer crust made of solid rocky material. It had a mantle made of silicate rock, solid rocky material. It had an iron core, the outer part of which was liquid iron, and the inner part was solid iron. And we had defined the depths of these various boundaries by the time of World War II or thereabouts. As we move closer to the present, we have a slightly different version. It's not that the first version was incorrect, it's just that we know more details now. And so the part that is important to our discussion today is that we still have the outer crust, which comes in two varieties. There's a continental crust and an oceanic crust. Below that crust is a part of the upper mantle that is strong and solid and supports the crust. Below that is a part of the upper mantle called the asthenosphere, which is also solid, but it's hot enough so that it is weak enough so that it's able to flow, kind of like silly putty. The mantle is entirely solid except in teensy weensy little places here and there, but we can think of it as being entirely solid, and so the only liquid layer of the Earth is the outer core before you get up to the surface with some oceans. So what we are going to talk about mostly think about when we talk about plate tectonics is a layer called the lithosphere. It's the crust and the uppermost solid and strong layer of the upper mantle. And so plates are pieces of the lithosphere. Now you can learn more about this by going to the IRIS video Earth Layers, and there's the link. You can pause the video and jot that link down, but that's a video that helps a lot. At any rate, we have determined by looking at the distribution of earthquakes and volcanoes around the Earth and by other means that Earth's outer surface is made up of a number of fragments like broken pieces of an eggshell, and we call these things lithospheric plates. And we happen here in North America to sit on the North American plate. The largest plate is the Pacific plate, and Africa is on the African plate, which is actually subdivided these days into a number of smaller plates. The details aren't terribly important. We could certainly go on for an entire course on plate tectonics, but here's the general picture. Each one of these colored areas is in motion laterally relative to one another. In some places, the motion is one plate colliding with another. In other places, it is one plate moving apart from one another. And in still other places, it's one plate moving essentially parallel to the common plate boundary and just more or less sliding past one another. So these are the three basic kinds of plate boundaries: convergent, divergent, and transform. Here are two more videos that you can take a look at, and you can pause the video to jot down these URLs. The first one shows a reconstruction of how plates have moved in the last 200 million years, and the second one is another IRIS video that goes into the three types of plate boundaries. So one of the types of plate boundaries involves convergence, one plate moving towards another plate, and if one of the plates is a plate that is topped by oceanic crust, slightly denser than continental crust, that plate tends to subduct, go underneath the other plate, which may be a lighter continental crust as it's drawn in this picture. This process of one plate dipping down and plunging into the mantle is called subduction. Divergent and transform boundaries are fairly simple. Here I have two plates, a green plate and whatever the heck that color is, and they are moving apart from one another, and part of the boundary here is a place where the two plates are spreading apart and new crustal material is being added to the trailing edge of each plate. These things are mid-ocean ridge spreading axes. Okay, here's one, here's the other. Now this series of spreading axes along a mid-ocean ridge appears to be sort of offset. Well, there's a little step here, and that's a ridge-to-ridge transform fault. Here's a ridge, and there's a fault in between the two, a place where a surface along which there is shear displacement, sort of like rubbing your hands together. We call that a transform fault, and that's a transform plate boundary. So as we move forward and try and put all these pieces together, I want to show you a model that has been around since about the mid-1980s. And we imagine that on a sphere, each one of these plates is sort of moving around a pole of rotation. And so on a sphere, if you make any kind of a lateral move, it can be expressed mathematically as a rotation. So each one of these plates has its own sort of rotational pole over time. The red curve here is the boundary between the two plates. And so let's just see what would happen if this plate rotates around this little green pole here, and the right plate rotates around this little pole here. And so we'll move this forward by a step. So it's spread apart a little bit. So in these places where you can see the gray in between, that is where the mid-ocean ridge has one of these spreading axes, and new material is being added to the trailing edge of the right plate and to the trailing edge of the left plate. And about the same amount of material is added to both of these plates. So these plates are growing along this axial spreading center. Simultaneously, along these boundaries, the two plates are moving past one another, more or less smoothly, although there's a little bit of gapping and a little bit of overlap along these things. But these are called transform faults, and they exist between these ridge axes. Fault, ridge, fault, ridge. Okay, let's take another step. A little further, a little further. Now this red line that you see is the original position of the plate boundary in the very first slide. So you can see that these plates are moving not only relative to each other, but relative to where they once were. Both of them a little bit closer to that red pole there, and so forth. So the transform faults are moving, the ridge axes are moving, the plates are moving, and so the picture that emerges from this is that plate tectonics is an enormously fascinating study of complicated motions on the surface of the Earth. These motions affect us in North America because we have kind of a complicated plate boundary on our western side, where this blue line is with little barbs, these little triangular things. That's one of those subduction boundaries. So there is a little plate called the Juan de Fuca plate, JF, that is slipping towards North America and diving down underneath North America. That subduction is the cause of the Cascade volcanoes. Mount St. Helens, Mount Adams, Garibaldi, and Baker, and Rainier, and Shasta, and all the rest of them. A little bit further off the coast is a mid-ocean ridge, okay? And the little red segments here are places where the ridge is spreading, and the little green segments here are transform faults. So there's this teensy-weensy little Juan de Fuca plate, and it's subducting under North America. Beyond the Juan de Fuca plate is the giant Pacific plate, the largest plate on Earth, and it's moving in this direction relative to the core of North America. And so the western part of the United States from Mexico up towards Cape Mendocino in Northern California is fundamentally something like a transform boundary. It's a complicated transform boundary, but that controls the earthquakes and the faulting and the tectonics of this particular area. If we move up towards Alaska, there's a great big subduction zone where the Pacific plate is diving down underneath Alaska. And so Alaska has the largest number of earthquakes of any state in the United States, and that subduction zone is a big part of the reason for that. So how do we know where plates are moving? Well, first of all, we can measure the motion of plates relative to each other using analysis of faults and some basic surveying techniques, basically. We can look at the motion of plates relative to hot spots. And so you wonder, well, what the heck is a hot spot? Well, it's a place where heat energy from the mantle essentially burns a hole in the lithosphere as it's passing over, and it leaves a mark that allows us to resolve the velocity of the plate relative to the lower mantle. To learn more about that, you should look at the IRIS video hotspot volcanism, a thermal plume. So pause the video, jot down that URL, but let's move on. We can also use high technology like very long baseline interferometry, where we use radio telescopes focused on a distant source of radio signals out in the far end of the galaxy, and we do sort of a triangulation problem. If we point radio telescopes on different continents, different plates at the same radio source and do it over and over and over again, you can see that the one side of that triangle is starting to get longer and longer or shorter and shorter because of these very detailed measurements that we can make. We can also detect plate motion using satellite laser range finding. Again, we take a powerful laser mounted at an observatory on two different plates, and we bounce it off of a little reflecting ball that we have out in space, the LEGEO satellite, and pick up those pulse signals at a different observatory on a different plate. And over time, we can resolve the change in distance between those two observatories. And finally, and very commonly these days, we use the global positioning system, the same GPS that is in your phone and probably in your car that helps you understand where exactly on the surface of the Earth you are. We have these GPS stations that we have built, very high resolution GPS receivers that allow us to calculate where this site is within really millimeters, certainly within centimeters, but millimeters over the course of a couple of decades, and that allows us to chart the motion of bits of crust really every place where we have one of these. And there are now probably more than 10,000 of these GPS sites worldwide. Here in the United States, we have a network that has been operated by UNAVCO. It was once called the Plate Boundary Observatory, created during Project EarthScope, and it has collected a couple of decades worth of data. And these little blue vectors indicate the direction of motion of some of these PBO GPS sites over that period of time, the average motion of those sites relative to the deeper mantle. So these days we are quite sure that the Earth's surface is in motion, and it helps us to understand the development of earthquakes and volcanoes and a number of other important geological phenomena.